Welcome back to the Deep Dive. Today we're digging into something you use constantly, maybe without even thinking about it. Natural language processing, NLP. Asking your phone a question, getting text suggestions. AI is reading and writing language all around us. Okay, let's unpack this. How do these machines actually understand us?
Yeah, that's exactly what we're tackling. Natural language processing, how AI, interprets processes, even generates our language. We'll look at how it works underneath, some pretty surprising things it can do. But also, and this is crucial, where it falls short. What are the limits? We're drawing on work from top AI researchers, foundational texts, looking at everything from spam filters to the big quest for AI common sense.
Right, so let's start right at the beginning. Computers think in numbers. Language is messy, right? Words, meanings, feelings. How did that translation happen?
Yeah.
The basic idea is turning text into numbers the computer can work with. It's called a feature vector. Think of it like giving every single word in a huge dictionary its own unique ID number. So a sentence just becomes a list of numbers.
hmm And it wasn't always done this way. The very first attempts, way back, were quite different. They used what are called symbolic, rule-based systems.
Hmm.
Basically, people tried to write down all the rules of grammar, like huge lists of if this word, then that structure. But language is just too subtle, isn't it? Full of exceptions, context. These
Well,
rigid rules, they were just too brittle. They broke easily. So by the 90s, the field pretty much moved on, realized you couldn't just hard code language like that. What's fascinating here is how quickly the field moved past rigid rules once it embraced the power of data. Letting the machine learn from examples, that was the shift.
okay, so learning from data, and that leads to things we see every day, like spam filters. How does my email know it's junk?
Right, spam detection. That's a classic example. Often it uses something called a support vector machine, an SVM. You can think of an SVM as trying to find the absolute clearest dividing line between two groups of things. In this case, spam and not spam.
So it takes the email text, turns it into that number vector we talked about.
Exactly. Converts the text into numbers. Then the SVM does a bit of math to see which side of the line that email falls on. +1 for spam, -1 for not spam, something like that. It's all about finding the biggest possible gap, the highest margin between the two categories. Makes the decision clearer.
Got it. Okay, so that's classifying emails.
hmm
What about understanding like emotion in text,
Yeah.
sentiment
Yeah,
analysis?
sentiment analysis, figuring out if, say, a movie review is positive or negative. And that's trickier than it sounds. You can't just look for keywords like dark or weird because those words could pop up in a really positive review, right? A dark, gripping thriller. Context is everything.
So simple rules fail again. How do they handle that sequence, the flow of a sentence?
That's where things like recurrent neural networks or RNNs come in. They're designed specifically for sequences, like sentences. They read word by word, and as they go, they build up and update this kind of internal summary and encoding of what the sentence means so far, so they can actually capture that context, the nuances that build up over the whole sentence.
Okay, that makes sense. Building understanding word by word.
And then there was another huge step, word embeddings. This is really cool. Imagine mapping every word to a specific point in a kind of high-dimensional space, like coordinates. Words with similar meanings, or words that tend to show up in similar sentences, end up closer together in this space. So semantic distance, how similar the meanings are, becomes the same as geometric distance.
So like king and queen would be near each other but far from banana.
Exactly. Systems like Word2Vec learn this just by looking at billions of sentences. They noticed book, paper, article appear in similar contexts, so it puts their vectors close together. If we connect this to the bigger picture, this allows machines to grasp relationships between words in a way that's quite intuitive for us. It led to those famous examples like you could do math on the word vectors, take woman, subtract man, add king, and the closest vector you'd get would be queen.
Wow, that does feel like understanding.
It feels like it. But here's the catch, a really important one. These systems are amazing pattern matchers, but they don't have real-world common sense. I actually played around with one of these online demos. If you ask thirsty is to drink as tired as to, what do you think it says?
Sleep.
It might say drunk, or fish is to water as bird is to. It might suggest hydrant,
Hydrant, why?
because statistically, maybe tired and drunk appear together sometimes in the text it learned from. Or maybe bird and hydrant showed up near each other for some random reason. It sees the co-occurrence, the pattern, but it doesn't understand the reason. Thirst causes drinking. Fish need water. Birds don't live in hydrants. It misses the underlying meaning, the real-world knowledge.
Okay, that's a crucial difference. And if it struggles with word meaning, what about spoken language? Voice assistants, Alexa, Google Home. Here's where it gets really interesting.
Huh.
The leap from text to spoken language, they seem so accurate sometimes, right?
They are impressively accurate, yeah, especially in quiet conditions for common phrases. Maybe 90–95% of human accuracy sometimes. But that human-level claim you sometimes hear. Well, contrary to some reports, it's not quite the whole story. They still have trouble with background noise or, unusual words or accents.
And they make mistakes that just seem silly from a human perspective.
Exactly. Like, you might say, moose is my favorite dessert, and it writes, moose is my favorite dessert.
Right, because moose and moose sound the same.
Or the bareheaded man needed a hat becomes the bareheaded man needed a hat. These aren't just typos. They show a lack of understanding of the speech they're transcribing. The AI doesn't know what moose is, or a moose, or the difference between bear and bear in context. It lacks that connection to the real world, what some call grounded cognition.
That makes sense. This is processing sounds, not meaning.
Yeah.
And we see similar things in machine translation, don't we? It's come a long way from those really brittle rule-based things. Now it's statistical, data-driven. Google Translate, Microsoft. They even claimed human parity a few years back.
They did, around 2016. And the improvement was dramatic. But human parity might be overstating it, especially with nuance.
Yeah, there's that famous restaurant story example. Someone translated a simple story from English to Italian and back using Google Translate. Instead of cooked rare, it said cooked infrequent. Burned to a crisp, got burned at a crunchy.
Got burned at a crunchy.
And the best one, the bill, the check became the proposed legislation.
Oh, dear. Right. Because bill can mean different things. It shows the system doesn't grasp the context of being in a restaurant. Or idioms like burn to a crisp. It's matching patterns, not understanding the scenario.
And this isn't just funny, right? Think about automated image captions. Microsoft's Caption Bot, Google's Show and Tell. They can be amazing. A dog running through a field, perfect. But sometimes they're just bizarre, completely wrong.
That bipolar performance, as some call it. Magical or nonsensical.
And if someone blind is relying on that caption, getting it wrong isn't just funny, it could be dangerous. Accuracy without understanding is risky.
Absolutely. Which brings us to chatbots and question answering, like IBM Watson winning Jeopardy back in 2011. That was a huge moment.
It really was. Felt like a major leap.
It was an incredible feat of engineering, no doubt. Watson could process the clue, search vast amounts of data like Wikipedia, and find statistically likely answers incredibly fast. But the AI community itself was kind of split. Was it a true advance in understanding or more of a publicity stunt, a really impressive parlor trick?
Because it was trained specifically on Jeopardy clues.
Right.
It learned the patterns of those questions.
Exactly. It learned patterns from hundreds of thousands of clues, all with a similar format. It was brilliant pattern matching on a massive scale. This raises an important question. Was Watson truly understanding the questions, or was it a very sophisticated pattern-matching machine? David Ferrucci, who led the Watson team, gave a great example later. If you tell an AI, the printer is broken, what should it do?
Tell me how to fix it. Offer to help.
Right. But current systems often perform poorly on that. They might identify printer and broken, but they don't get the purpose behind you saying it, the intent. Ferrucci said they ignore the intentional structure component of dialogue. You're not just stating a fact, you have a goal, get the printer working. Current AI often misses that social intentional layer.
That idea, intent, of purpose, that feels like a huge gap. And it leads us to the really deep challenges, doesn't it? The final frontier.
Yeah.
Common sense, abstraction.
Precisely. Humans have this vast core knowledge about how the world works. Gravity, objects, basic physics, social rules. And we build mental models. We can reason flexibly. There have been attempts to give this to AI, like Douglas Lynach's huge, decades-long psych project, trying to manually write down millions of common-sense facts and rules.
How did that turn out?
Well, psych has some commercial uses, but it's generally seen as being narrow rather than general in focus. It's a giant database, but it doesn't seem to have that human spark of, like, abstraction and analogy making. It knows facts, but can't reason flexibly like we do.
And there are tests specifically for that, right? Those Bongard problems.
Yes, Bongard problems. They're visual puzzles. You see two sets of simple diagrams, and you have to figure out the abstract rule that distinguishes set A from set B. Solving them requires the same kind of abstraction and analogy skills humans use all the time, and that a truly smart AI would need.
So how do current AI systems do on those?
Terribly, actually. Even powerful image recognition AI, the convolutional neural networks, give them 20,000 examples of Bongard-like problems, trying to teach them same versus different based on abstract properties, and they perform only slightly better than just random guessing. Humans often get it right after seeing just a handful, maybe 12 examples.
Wow. That's a huge difference.
It really is. It shows how bad current systems are at conceptual slippage, seeing the underlying similarity or rule even when the surface details change. They get stuck on the surface patterns.
Okay, so common sense and abstraction are major hurdles.
Yeah.
What about just knowing why the AI gives an answer? The black box problem.
That's another massive issue. Deep learning models can be incredibly complex, millions or billions of connections. They give you an answer, but it's often impossible to trace back why they reached that specific conclusion. It's a black box. This makes it hard to trust them for high-stakes decisions,
Yep.
medical diagnosis, loan applications, self-driving cars. If it makes a mistake, how do you fix it if you don't know why it happened?
And they can learn the wrong things too, right? Overfitting.
Exactly, overfitting. The model learns quirks or irrelevant patterns in the training data instead of the actual concept you want it to learn. Like maybe all the pictures of animals in its training set happen to have blurry backgrounds. So it learns blurry background means animal rather than learning what an animal looks like. It works perfectly on the training data, but then you show it a clear picture of an animal and it gets confused.
And then there are those adversarial examples. Those seem really worrying.
They are. These are tiny changes made to input data, maybe changing a few pixels in an image, putting small stickers on a stop sign, slightly altering an X-ray, changes that are often invisible to humans. But they can cause the AI system to completely misclassify the input, often with very high confidence.
So a stop sign becomes a yield sign, or a benign tumor looks malignant to the AI.
Potentially, yes. It shows a fundamental brittleness, a difference from how human perception works, and is a huge security risk. So yeah, current deep learning is amazing for specific tasks, mostly pattern recognition where you have lots of labeled data, but they're narrow and task-specific. They are definitely far from achieving general understanding or common sense reasoning. What's fascinating here is that despite incredible progress in specific tasks, the true understanding that enables generalization and common sense remains largely unsolved.
Right. So looking ahead, deep learning is powerful, definitely a wonderful technology, but it sounds like it's just one tool in the toolbox. Maybe not the only answer.
That's what many researchers think, yeah. That future progress probably needs integrating ideas from other spheres of artificial intelligence, combining deep learning's pattern matching strengths with maybe more structured knowledge, more explicit reasoning capabilities, not just bigger neural networks.
Towards something like artificial general intelligence, AGI.
That's the long-term dream for some, yes. AGI, a true thinking machine with human-like flexibility across many different domains. And a lot of people think unsupervised learning is key. Getting AI to learn more like babies do just by observing the world, interacting, figuring things out without needing millions of pre-labeled examples for every single concept. That's seen as a really promising avenue, but also a major hurdle to achieving AGI and genuine common sense.
And important to remember, these systems aren't actually trying to be brains, right?
Correct. They're inspired by some of the brain's computational characteristics, sure, but they are not trying to imitate the brain directly. They're sophisticated statistical models. And, as these tools get more powerful, we absolutely have to talk about the ethics right now. We need to think about unintended consequences, how biases in data can lead to unfair AI decisions. We need ethics integrated into computer science, thinking about how to ensure these AI systems would be good for people in the world.
So what does this all mean for you as the user of these increasingly intelligent systems?
It means recognizing both the power and the limitations.
Okay, so we've gone from how machines turn words into numbers through spam filters, translation, voice assistants, seeing the power of pattern matching, but also hitting those walls, the lack of real common sense, the brittleness, the struggle with true meaning and intent.
Exactly. This deep dive today reveals that while AI is incredibly adept at processing language, its understanding is fundamentally different from ours. It's often a brilliant form of statistical pattern matching, but it lacks that grounded, causal, common sense reasoning that we humans rely on constantly. So here's something to think about. As AI continues to advance and these systems become more integrated into our lives, what stands out to you about the difference between a machine processing language and truly understanding it? It's a fascinating area and definitely worth keeping an eye on.